Okay, this is the first video in the probability functions section, which is an introduction, and it's basically an introduction to the concept of random variables, how we handle those with probability functions, and what we mean by expectation and so on. Let's crack on. Okay, so what is a random variable? I mean, this is a great description I picked up from somewhere. Random variable, sometimes called a stochastic variable, is a type of variable in statistics whose possible values depend on the outcomes of certain random phenomenon. Since a random variable can take different values, it's commonly labeled with a letter. That's a capital X. Each variable possesses a specific probability distribution function, which describes the various probabilities of the different values of the random variables. And we've got two main types of random variable that we want to look at. There's discrete and continuous. Discrete are the functions that go with them tend to be called mass functions, and those continuous as density functions. We'll kind of see what we mean by that in a moment. What could it be? So the examples, the value on the face of a rolled dice. So roll a dice. It can be 1, 2, 3, 4, 5, or 6. What is the probability of getting a 3? What's the probability of getting an even number? The value of a flipped coin. Now, obviously, it's head or tail, but normally we would assign a numeric value to these different possibilities. For instance, 0, 1. The height of a randomly chosen person in meters. So we just pick someone on some basis, somebody in the street, or we put all the names in a hat and then pull somebody out and measure them. You know, this sort of thing. The length of life of a light bulb. There's an interesting one, and a number of people arriving in a given 1 minute interval at a railway station. Again, so something that could be, small, could be large, could be 3, could be 50. Okay, so and when we write these probabilities down, this is a sort of notation we tend to use. The probability X equals 3, the probability that this random variable is equal to a particular value. That would probably be for a discrete probability. Probability that the random variable falls between 1.68 and 1.78. That could be the height example, couldn't it? Could also be discrete, but probably continuous. And then more generally, the probability that the random variable is greater than some value. This little notation is a little bit confusing because we're using X twice, but X is the random variable and little x is the particular value that we're referring to in the context of what we're saying. Okay, so that is generally the idea of random variables. Let's have a look how we might describe these in terms of probability functions. Well, so let's have a look at some discrete random variables. For starters, well, this would be a very simple, straightforward way of doing it. We've got a random variable that can take 4 different values, 0, 1, 2, 3, and each of those has a probability. Now, the point here, of course, is that all these probabilities must add up to 1, and if we were to add those 4 values, we would find that equals 1. And here we're saying probability that the random variable takes the value x is, for x equals 0 is this, for x equals 1 is that, and so on. Here's another one. This is if we roll a fair dice, then there are 6 values and they all have equal probabilities, and that probability is basically 1/6, which is shown on there. Excuse me. And then here's one bit more sophisticated, perhaps. This is a random variable that can take, well, 21 different values. from 0 up to 20 inclusive. And the length of this line vertically gives the probability of the random variable taking that value. So the probability that random variable takes the value 4 would be, well, that's something like 0.19, isn't it? And so on. We can read that. These probabilities are all very, very low. And we'll see this particular shape come back later. And then let's just a little more space. As far as continuous probability functions are concerned, then, well, these are described by a density function. I talked about density functions before. So, so here we've got a function which is, well, it's a value of 1 over b minus a between a and b. So, and the point there, of course, is that this means that this total area under the, say, curve, straight line, it's a curved line, a curve of a sort. So that's a total one. So if we were to say with the continuous random variables, we don't talk about what is the probability of a specific value, because any specific value, its probability is infinitesimally small, so it doesn't make sense. All we can do is talk about the probability that the random variable falls into a range. And of course, if we were to say, what's the probability that the random variable falls between a and b, well, of course, it would be the area under the curve between a and b, which of course is 1. So the whole thing. But we could take any subset of this from here to here and measure, or calculate more likely, the area under there, and so we could actually work out the probability of that. We've described this function like this. So the function is 1 over b minus a between a and b, and 0 otherwise. So that, and this particular thing here is basically a continuous uniform probability function. This one, incidentally, is discrete uniform. This is a continuous uniform density function. Okay, so yeah, so basically we pick our values, and if we want to find the probability in that range, then basically it's the area under the line between these 2 points. And here's another one. Now this one is going to come up. You're going to see this one over and over again in this probability functions section. This is a normal probability function. And here it's, this is a, what am I call standard, because it's got a mean of 0 here in the middle. And again, likewise, you know, we can measure the probability that this random variable falls between -1 and 1 simply by measuring this area like that. Or the probability that it's greater than 2 would be this area in this little tail over to the right. Okay, so the equation of this curve is actually this weird and wonderful thing here, where the mu is the mean of the population, and sigma is the standard deviation. So it's got this more or less, well, it's got the same shape. It's just that the scale and central point will actually vary. So so that is that. Now we don't really have to worry about this. I mean, in theory, if you wanted to find the area above 2, then you know, you can have to integrate this between 2 and upper limit of infinity and 2. So if you know anything about calculus, I think you will know that that's actually quite a difficult thing to do. But no worries about that, because all that's been done for us and put either in tables or more usefully nowadays onto your calculator. So if you go to ClassWiz calculator and use menu 7, all this stuff is already there for you. So these are examples of continuous probability functions. Okay, what else have we got? All right, so what we're interested in with these probability functions is a couple of the key parameters are the expectation. So the expectation is it's weighted mean of all possible values. So what we're looking at is we're saying, well, let's take all the values and multiply each one by its probability, and add all those up. So by way of example, going back to the roll dice, and then what we would do is we would actually take, well, the value 1 has got a probability of 1/6, 2 has 1/6 as well, as does 3, 4, 5, and 6. So if we work this sum out, it gives us 3.5, which seems eminently reasonable, doesn't it? Because that's sort of like the midpoint, if you like, of 1, 2, 3, 4, 5, and 6. So that would be the expected value. Okay, we also measure this is very much like the mean, of course, when we're talking about in the data section. It's a sort of equivalent, and kind of one way of thinking about probability functions, and also the things that we discussed in data. Data tends to be about data that you've measured, that you've already measured, whereas probability functions tend to be about things that haven't happened yet, and we want to understand the probability of them happening. But within all that, there's actually quite a lot of common ground and similarities. Okay, we're also interested in the variance of a random variable, just as we are in the variance of data that we've actually observed. And to do this, well, this looks a little bit familiar with what we've done under data. So it's basically the expectation of this difference, the square of the differences of all the values from the mean, which, when we do a bit of maths on it, basically is this. Now, this does look a bit like the mean of the squares minus the square of the mean. So it's the equivalent, basically. So what we want is the expectation of x squared minus the expectation of x all squared. Now, to find that first one, and we've already got the second one, haven't we? Expectation of x there. Just want the first one, expectation of x squared. So what we do is we take the square of each possible value and multiply by the probability of that value. 2 squared times 1/6 and so on. If we work that out, that comes to 15 1/6, and therefore the variance would be 15 1/6 minus 3.5 squared, which works out to be this 2.9. So that would be the variance of the random variable that describes the rolling of a dice. All right, so now I don't have to worry about this too much, but again, if you've done some calculus, then this will be some meaning to you. If not, then don't worry about it. It's not something that's going to immediately trouble us, but yeah, if we're finding our expectation by multiplying the value by the probability and adding them all up, we've got a continuous random variable, then obviously this kind of doesn't make sense. We've already said that the probability of a discrete value is, unspecific value, has no meaning. But what we're actually doing equivalently is actually doing this. We're summing these things in the limit as our intervals get smaller and smaller and smaller. So the result is this is the integral of x times f of x being the function, which we can only do obviously if it's some kind of continuous function. With respect to x, and then we got a similar thing for the variance, so we would have to evaluate this. Anyway, we can, it's just to be aware of at this time. There'll be the odd example video that actually evaluates this, but that's probably as much as we need to know at the moment. Okay, transformation of random variables and variance. Just a few things to know when we talk about variance, because the variance of a constant, a random variable, can only take one value, you could say. Then the variance is going to be 0. That's fairly straightforward, isn't it? If we couldn't take our random variable and we can sort of morph it somehow, we can scale it up, we can shift it, by adding a value to it. If we do that, if we were to shift it, we could say this is a new random variable. This x plus a, could call it y, but it's basically shifted. Well, it doesn't change the variance basically. If we just shift a random variable, then it doesn't change the variance. However, if we stretch it by this, say we've got a random variable, say the dice example. So say we want to multiply, we want to form this new random variable, which is 10 times the value on the dice. So we got this new random variable ax. Just so we could call y if we wanted. Well, actually, because variance is a square measure, then what we're actually doing is we're multiplying it with whatever the variance of x is, and we worked it out just above, didn't we? 2.9, there we go. So this would be 100 times 2.9. So that's something to bear in mind, because that sort of thing does come up. The other thing, again, just to be aware of, not really to worry too much about at the moment, is that we do have the idea of sort of two-dimensional probability functions, and therefore we will have covariance of this pair of random variables. So we have a way of dealing with that, and then we've got a corresponding formula here for all that. So yeah, it's basically around this thing called a covariance. So that is pretty well it, really. So I think if you've followed that through okay, hopefully you have, then you'll have a reasonable idea what we mean by a random variable, and obviously the idea of probability functions, probability mass functions, probability density functions for continuous random variables. The distinction between the two isn't going to bother you too much. You will be interested in whether or not it's continuous or discrete, but mass or density is a bit of terminology, really. Okay, so hopefully that has been useful, and we'll get into the details of probability functions in the next video. So I will see you then.